कोई भी answer. Why should I talk about it? Answers can be right, but whether they are relevant or not, that's a different thing. You can give the answer that GIAN ਦੇ ਕੋਰਸ 'ਚ ਤੁਸੀਂ ਆਏ ਹੋ, ਤੁਹਾਨੂੰ ਜੌਬ ਦਿੱਤੀ, ਤੁਸੀਂ ਫਿਰ ਕੁਝ ਕਰੋ. That can be very correct answer, but it's irrelevant. ਜਾਂ ਤੁਸੀਂ ਇਹ ਕਹੋ cells in the body, relevant. Answers can be right. They also need. Maybe you don't know that why to talk about that, or do you know? If anybody knows, does anybody know what I have been doing in my life? मैं जी एजिंग पढ़दा मारदा रहा, गाने गाता रहा. Yeah. आज ज़्यादा ही आ गया पानी. Yeah, because models, and one model is cell culture. Yeah, that you can do aging research by using cells in culture, which she left out yesterday deliberately because she thinks that I can maybe talk a little bit more about that. And the reason is, okay, I will tell you the story of the reason. ਜਦੋਂ ਮੈਂ 6 ਸਾਲ ਦਾ ਸਾਂ, story always starts from the beginning. So when I was 6 years old, there was a paper published in 1961, Serial Cultivation of Human Diploid Cell Strain. ਉਸ ਤੋਂ 4 ਸਾਲ ਬਾਅਦ ਇੱਕ ਦੂਜਾ ਪੇਪਰ ਛਪਦਾ. Those two papers were the most cited papers actually. That was the guy Leonard Hayflick. So the citation index, so he has 30,000 citations. He has H index of 62. And those papers changed the whole scene of aging research. Okay. Unne show kita that if you grow normal cells in culture, they cannot live forever. And he had big problems publishing the first two papers between 1961 and 1965. Nobody believed that result. What do you think may be the reason? Yeah, he was a young postdoc at that time. He is now 92. We actually share even birthday. We are born on the same day, but the year is different by 50 years or longer. You think that that observation was rejected by most of the world scientists, Nobel laureates and other people. But he insisted that if you grow cells outside the body, they have a limited lifespan. We all know that bodies have a limited life. But why do you think people were rejecting it? You may not know the history, but I'm asking, what do you think? पर जो बाहर करते हैं तो उसमें but why they do not divide all the time? Because okay, उसका hint का कि until then actually there were lots of studies being done on cell culture. Cell culture basically started in 1910, yeah? And there were people who were never cells were growing on and on. So that was a well-established fact that if you cells outside the body, somehow them right conditions, ठीक media दोगे, cleanliness रखोगे, they will carry on dividing forever. Now that was based on the observation or the fact, Professor Alexis Carrel, जिन्होंने he got Nobel Prize in 1920, ਉਹਦੀ lab 'ਚ ਇੱਕ ਉਹਦੀਆਂ data ਜਿਨਾ ਤੁਹਾਡਾ ਜਿਵੇਂ ਤੁਸੀਂ ਕੱਲ ਚੈੱਕ ਕਰ ਰਹੇ ਸੋ ਨਾ, so किधर जे मौका मिले कर लेना check because sometimes I mix the day, so years may be up or down, but it's not a huge difference. So in his lab, they were growing chick embryo fibroblasts, the fibroblasts from the chicks, and they were growing continuously for about 40 years. Papers, and they were always draw the curves. The cells are growing on and on and on. As a result, and he got Nobel Prize. And everybody also thought that, yes, they are immortal cells. And in around 1945 or so, then this HeLa cell line was created. Yeah? Hila, you know what's the meaning of Hila? ਇਹਦੇ ਉੱਤੇ ਫਿਲਮ ਵੀ ਬਣੀ ਹੋਈ ਹੈ ਹਾਂ ਓਏ ਹੋ ਜਿਹੜਾ ਵੀ about her recently. She was Henrietta Lynette or something, so a black woman, but that was from a cancer tissue, from cervical carcinoma. But then the difference between normal and cancer was not even clear. So say if you take the cells out, they will live longer, as long as possible, especially these chick fibroblasts. So when I also went to do my PhD job in Holiday, my first assignment by him was, again his style, not giving me the answer, go and read papers by Alexis Carrel from 1920 onward and see what are they saying it. And now you want to work on the aging of cells. Was he right or was he wrong? So that's where the sociology of science starts coming. So when I read his paper, so he also had the same kinds of graphs I will show you, where cells are growing and some cells will die out, but some will. And he was ignoring the fact when they were writing the paper, some of our cells died due to technical reasons. And then some other cells will continue to grow. But that was so dominant that when Hayflick sent this paper to experimental medicine research, whose chief editor was Rouse, in a Rouse sarcoma virus, the discoverer, he sent the letter back by saying that so far the only truth in biology is that cells outside the body do not die if you give them right conditions. And there is a person who is creating the claim that if you grow the cells, they will die in a certain number of times of division. So but then there was a new journal, Experimental Cell Research, just started in Sweden. So he sent that paper to them and they published it. So next 4 years it took to reproduce the data by sending the same cells to 20 laboratories in the world. Okay, tusi grow karke dekh lo. And then the data started coming after a few months ago. Our cells are dying. They are looking like the pictures you have published there. So what is going on? So that was basically the start of the field of aging. Before that, it was aging at the cellular level. It could have started in 1910. So it started from 1961, 1965. So the whole science was made by almost 50 years. So what with the Alexis Carrel's experiment go wrong in our laboratories? Sanjay? थोड़ा ऊंची बोलने की कोशिश करो ताकि वो उठे बैठी नू भी सुने. Yes, valid explanation. Any other explanation? Because that was not what was found to be real explanation, but that's a valid thing, that they were working with already cancerous cells. But because they were working with embryo fibroblasts, that was not the issue, because chicks are usually from embryonic fibroblasts, the cancer cells are, well, they can be there, but that's not easy. So you can look at it. Right. Those phenomenon or that you usually see in rodent cultures, less in chick cultures, but rodent cells, they mouse, they rat, they cell grow karna, they become, there is a special term for that. Yeah, spontaneous transform. Without giving them any drug, without giving radiation, there's a very high spontaneous transformation frequency of these rodent cells. There are reasons for that, but before TT large and radiation or do drastic things. So then what was this other possibility? Yeah, human difference. So you think that the human cells were not right. So if they had given right conditions, or if Hayflick had given right conditions, but the concentration, serum the concentration, koi hor condition, air, jo kuch jo test kar sakde si, they tried to find when those explanations were ruled out. Then in the paper in 1965, Hayflick wrote that they think that in their cultures they were by mistake adding extra cells every time they adding new chick extract, because we didn't have high quality serum production. Now we cell culture, we use serum. So they were making the extracts from other chicks and putting that into that. So maybe some cells were being added by mistake. So original cells, when they were, but you are always adding fresh one and they take over. So that was Hayflick's explanation. But then 30 years later, in 1980, at Robbins Place. So some historical research. What was the reason? Because that's not enough explanation. If you take extract, that will give maybe few cells, and few cells cannot populate so much, so many flasks, aging. So then he happened to find out the two old technicians of the lab. Because that also showed another side of science. Just imagine, let your imagination run. And now those two old ladies who are not working, they might be dying very soon, they have nothing to fear. Yeah? When we are young, we don't tell truth often, because the power of the boss is very important. In those days, even in Western world, it was the same. It's even now same, they don't show it that quickly like it happens here. ਇੱਥੇ ਜੇ ਗਲਤ ਗੱਲ ਕਹਿ ਦੋ ਕਿ ਉਸ ਸਮੇਂ ਪ੍ਰਾਈਸ ਪੇ ਕਰਨੀ ਪਏਗੀ, ਬਟ ਉੱਥੇ ਜਰਾ ਕੋਈ ਸਾਲਾਫਾਤ ਕਰਨੀ ਪਏਗੀ. Yeah, almost. Those two ladies agreed that because Professor Alexis Carrel used to become so upset and angry ਕਿ ਜਦੋਂ ਵੀ ਉਹਨਾਂ ਨੇ ਜਾ ਕੇ ਉਹਨਾਂ ਕਹਿਣਾ ਕਿ ਸਰ, these cells are looking abnormal and they have stopped dividing, he will shout at them, you idiots, you don't know how to grow that, and blah, blah, blah. And then he's a big boss, he's a Nobel laureate. How... ਸੋ ਉਹਨਾਂ ਦੀ ਹਿੰਮਤ ਹੀ ਨਹੀਂ ਸੀ ਪੈਂਦੀ ਉਹਨੂੰ ਕਦੇ ਦੱਸਣ ਦੀ ਕਿ ਮਹਾਰਾਜ ਸੈੱਲ ਮਰਦੇ ਪਏ ਜੇ, ਕਿ ਪਲੀਜ਼ ਹੈਵ ਏ ਲੁੱਕ. ਹੁਣ ਬੌਸ ਕੋਲ ਤੇ ਟਾਈਮ ਨਹੀਂ ਆ ਕੇ ਮਾਈਕਰੋਸਕੋਪ ਦੇ ਥੱਲੇ ਆ ਕੇ ਆਪ ਦੇਖੇ ਵੀ ਕੀ ਹੈ, ਕਿ ਉਹਦੇ ਲਈ ਕਿ ਇਟ ਮਸਟ ਕੈਰੀ ਔਨ ਗਰੋਇੰਗ, ਯੂ ਹੈਵ ਟੂ ਪ੍ਰੋਡਿਊਸ ਦ ਡੇਟਾ. ਸੋ ਦੇ ਵਰ ਆਲਵੇਜ਼ ਸਟਾਰਟਿੰਗ ਨਿਊ ਕਲਚਰਸ, ਕਿ ਜਿਹੜਾ ਪਹਿਲਾਂ ਮਰਨ ਵਾਲਾ ਉਸ ਤੋਂ ਪਹਿਲਾਂ ਇੱਕ ਹੋਰ ਸ਼ੁਰੂ ਕਰ ਦਿਓ, ਉਹਦੀ ਫਿਰ ਚੱਲਦਾ. ਪੇਪਰ ਛਾਪਣ ਲੱਗਿਆ ਡੇਟਾ, ਪ੍ਰੋਫੈਸਰ ਕੈਰਲ ਵੀ ਛਾਪ ਦਿੰਦਾ ਸੀ. ਸੋ ਦੈਟ ਵੈਨ ਆਈ ਵਾਜ਼ ਰੀਡਿੰਗ ਮਾਈ ਫਸਟ ਅਸਾਈਨਮੈਂਟ, ਯੈਸ ਦੇਰ ਵਰ ਲੋਟਸ ਆਫ ਸੈਲਸ ਲਾਈਨਸ or cell strains which were dying out, but they will always say by mistake, by technical reason, by contamination, which happens, which is also true. But then only concentrate on this continuous growth because of the boss's expectation. Yeah, very serious in the present time, even more. So you have about that. The pressure is so much to produce papers, to produce data, to produce next grants, to come into the television. And the pressure is mostly on postdocs. And they make such sometimes arrangements. And if the data suits the teacher, so the teacher agrees, ignores it. The teacher may not have told the student that make this fraud. But students do the pressure. And that is how every year hundreds of papers get withdrawn. Okay, pressure in there. So that is a big, big temptation in our research. कि पहले तो अपने immediate supervisor ਨੂੰ खुश करना. जब कि science the principle ये है कि okay, one time the first supervisor may say no, well, do the experiment again. There is something wrong. But if you have done once, twice, thrice experiment and say no, this is what is happening every time, then you must stand by it. This is what the reality shows. Whatever your thing, if you want to make another graph, please go ahead and make yourself. So as a student, as a postdoc, try not to surrender your scientific honesty. It's not easy. It's not easy. It's not going to be easy. But otherwise, science gets affected so much. This particular say that aging research got delayed by 60 years. J. Alexis Carrel, the student, or the technician, we ehi observation to assert karde. We could have started the same questions much faster. So how the whole history of things became separated from the way we do things. So I'm telling this story especially because that's a very important story. Latest story in that action is 3 years ago there was a paper published by a Japanese PhD student, nature ਦੇ ਵਿੱਚ stem cells ਬਾਰੇ. ਹੁਣ stem cells ਦੇ ਤੁਸੀਂ interested ਹੋ, ਹਾਂਜੀ, ਆਹ ਤੁਸੀਂ stem cells ਦਾ ਕਿਹੜਾ ਸੀ ਉਹ paper which created a great controversy. Huh? Yeah. No, the paper which created a big scandal, that was a Japanese paper 3 years ago. It was published in Nature. Okay, so his stem cells interest, that's why I'm asking. Because that girl published a paper in Nature. Now look at the refereeing quality control. And the paper was that if you take any normal human cell and you change its pH, you put them in acidic condition instead of normal 6.7, 7.6 range which we use, if you bring it to pH 4.5 or 5, just for half an hour or 1 hour, and then bring them to null, they all become stem cells. Induced pluripotency without any transcription, without thing, just by changing pH. Oh, of course, the whole world got shaken. When the paper came, immediately I asked my student, hey, come on, is that the way to make a stem cell? That's the easiest thing. So of course, the whole world started repeating. Nobody was getting the data. Nobody the same effect. And they are then, first of all, they asked Nature people that, how come you have published this? It was so amazing that we wanted to be the first to bring in. So that was the pressure, commercial pressure. Nature So they ended up publishing, but no to repeat it, and within a week the whole world started talking about it. The girl was saying, that Japanese girl, that no, I have done it very absolutely correctly. Then several teams of scientists went to her lab, do it together. Nobody else could do it, even she couldn't do at that time. And she was saying, no, you are making me nervous, mere tension hai, to observe kar rahe ho ye. But we don't know what she was still doing, but nobody could reproduce, and she has always said that I have not cheated. But in 6 months, her supervisor killed himself. Only suicide because that's a Japanese culture. Yeah, because shame da bada vada issue hai na. Because oda to sara career tabah ho gaya na teacher da. Ke teacher de utte government lo firing ho ke sara world dekh raha hai. So that we don't know what has happened to the student. Of course, nobody in the world is going to touch her for any job. But she still says, no, I didn't do anything wrong. I did the right, and nobody knows the mystery. But it caused the life to the teacher. So ਕਈ ਵਾਰ ਤੁਸੀਂ ਟੀਚਰਾਂ ਨੂੰ ਵੀ ਜੇ ਉਹ ਕੋਈ ਥੋੜੀ ਸ਼ਰਮ ਦੀ ਭਾਵਨਾ ਹੋਵੇ, ਜੇ ਸ਼ੇਮਲੈਸ ਹੋਵੋ ਮੇਰੇ ਵਰਗੇ, ਘਰ ਦਾ ਚੱਲਦਾ ਕੋਈ ਗੱਲ ਨਹੀਂ. So that was the 1961 when I was just 6 years old. So that brought me into some career which reached its peak when I became 62. So in 62, the peak of my career was when, together with Hayflick, I brought a book. Hayflick and we then compiled a book inviting 17 people from the world to let's review this whole field. Yeah, because by that time I had become a scientist. I became a friend with Hayflick. We have been working together. We have been lecturing together. We have been publishing together. So in this series, which I bring, Healthy Aging and Longevity, we have many volumes. So one volume, 2 years ago, I brought together with him. So which I felt that's what the peak of my career is. So he might be dying anytime, but he generally keeps. I have lots of pictures I could show him, but we don't have time for today. So that is where we bring this book, and there is one statement which then Hayflick and I together write with it in the nice picture. Okay, what is the importance of this model system? That until these findings occurred, the focus of research on aging was mostly descriptive at the body level, and the causes of aging were thought to be driven by extracellular events. Because the body the aging hundi hai, cell the aging nahi hundi. If you grow cell, that means that there are some external factors. If you give proper conditions, then cells forever. But if you even give the reason, so this changed, that it is not just due to external events. With the discovery described cellular aging, the cause of aging for the next decades was redirected towards intracellular events. Okay, whatever is happening inside the cell. whether they are inside the body or outside the body, events are happening inside the cell. And that was a bigger intellectual jump. Okay, when you look for the aging causes, you don't have to look only at live happily, eat properly, or something that we can do so. So that was a great achievement of this study. And what is this model then? This model is basically what he first time published, which is a modified graph from his drawing, that if you grow diploid differentiated cells, they can be only subdivided a certain number of times. Yeah? That number of times can be, well, okay, we'll discuss that, what should that. But they will continuously grow, and slowly they will become slow, and eventually they will stop dividing. So Hayflick called it as a phenomenon of cellular aging. But whereas if you grow HeLa cells, they will not go through this curve, that curve will continue, and the immortal cells will never change. Yeah? So this phenomenon, later on, 10 years later, then Sir Burnett, the Australian developmental biologist, he then named it in honor of Hayflick as the Hayflick limit. Every cell, every normal cell has a intrinsic limit that after which it cannot divide and cannot live. So that was created as calling, because Hayflick never called it Hayflick limit. That's something in scientific research, in the basic research, we normally don't call any phenomena after the scientist name our cell. Hayflick will not call it, somebody else should call it. But whereas in medical terms, they give names to the diseases after the doctor himself gives them. Yeah, ਇਹ ਉਹਨਾਂ ਦੀ tradition ਹੈ medical ਵਾਲਿਆਂ ਦੀ. Alzheimer's disease is the one which Dr. Alzheimer never had it. ਉਹਨੂੰ ਤਾਂ ਨਹੀਂ ਸੀ ਹੋਈ ਨਾ. Oh, he was the first person to report the case. Same thing about most of the medical diseases are named after individuals, whereas the scientific research is less often. Somebody else has to give the credit. Then the whole phenomenon was termed as Hayflick phenomenon. So Hayflick phenomenon and Hayflick limit is the phenomenon observed mostly in cell culture, which is a very, very powerful tool to study why lifespan of cells is limited. And is it limited only outside or inside also? And what over the years then people started doing. So when I went for my PhD with Robin Holliday, that was the model system given to me. So Robin Holliday's lab was working on that. That okay, theories. So I was trained in that field from 1979 to 1982, and since then I have only worked on that model system. So perhaps that's why Gurcharan wanted me to talk with you, that at least you have the experience of a person who has spent 40 years with that model system. And that is where we have learned almost all modern molecular gerontology, the aging. They have mostly been understood from the Hayflick model. That has, because you could do work in the human system, yeah? And then you don't have to justify that, okay, this has implications. At least the system will, I will now ask you then what are the problems. Okay, human system, so what did we find out? Okay, this was one. This is the most common, first of all, the observation. That if you grow cells in culture, so these are from my own labs, that when we call them low passage, early passage, so sparse culture and confluent culture, these are skin fibroblasts. And if you keep on growing them in about 50 divisions, this happens. Yeah, from thin, long to very large. It's the same microscopic magnification, but it looks like from this and this, we have changed the objective. So, but that is the same conditions, but the cells have become very large, and there are so many effects are happening on that. This is the phenomenon, the Hayflick phenomenon, Hayflick limit, and this is the immediate appearance of cells. So an expert guy in the lab can see the difference between 2-3 population doublings, if you are seeing it, because every time a normal cell divides, something happens. It is pulled by one division. But it's very difficult to see the difference by unexpert, so I can see difference by every third or fourth passage or population doubling. Here the difference is almost, I think, 15 or 20 between one. So where it becomes clear. So that's what I'm going to ask them. Yeah. So what is the how to test the validity of the system? Then the first generation of scientists who then these big guys. So Len Hayflick himself worked a lot. Then his postdoc Vince Cristofalo. Now these are names that they don't mean much to you, but again in the history of science, when you study science, please see how science comes from each other. It's a very important historical trend. कोई भी उत्तो नहीं revealed नहीं ना knowledge. Everybody is aging. So Vince Cristofalo, American, he died 2 years ago. Alvaro Bachiria Coelho, he has just written another paper for my journal just last month. He's still active. He's about 83, 84. Sam Goldstein, he has died. Jim Smith, Olivia Pereira Smith, this was a team. Olivia is an Indian woman who is married to Jim, and together they really changed the field of aging by doing where is the aging happening, nucleus or fantastic experiment which only Olivia could do. Sidney Shell, a South African in England, still alive, but it doesn't work. That was the, and then they created students. So like I am the product of Robin Holiday School. So that is what then hundreds of us carried on working all our life, and this is the kind of data filled up. You are not supposed to read it. That's why in the book, this chapter on aging is the longest one, because that's where then, because I am teaching the course, so I go more detail there. People have measured everything from structural level to physiological level to biochemical level to molecular level. So we know almost everything why these cells age and how they age. And what have we learned? Basically, that ultimate phenotype, because right now everybody works on the last stage of cell culture, which is called senescence. And that is the result of all that table I was showing. There are thousands of changes happening at every level. Study only the last effect, which normally people literature, the reason will come in the next slide. But that is just the end point. The aging is this progressively happening phenomena. So cell culture showed that aging is occurring in cells every time they divide. They become one passage older. And then molecular level, then that what are the correlations, etc. That is what we know again. That there is no pre-programmed, no rigid Hayflick limit. There is a limit, but it's not predetermined. Again, fits with the general aging. That's where I've been talking about gerontogenes. They come from these studies. There is no program. And the loss is happening. Okay, there are correlations. DNA methylation and telomere. This is the most, telomere is more tested. Measure telomere in immortal. There are also correlations that yes, when cells are becoming older, they are losing telomere. So why should they lose telomere? Are they causing aging, or this is just a consequence of aging? These are very important observations. What else we learned from that? Yeah, but here until so far, the question which Gurcharan was trying to raise. So how to justify that aging of the cell in the laboratory is a representative of the aging in the body? So if you want to say, okay, show me that whatever happens in the body, in the aging of the cells in the culture. So what should we compare? Think about. Yeah. What is aging of the body? That okay, I am becoming old, either in terms of numbers or stages, whichever way. At some stage, somebody is young, somebody is old. Yeah. So can we use that difference in measuring or testing Hayflick system? Sorry, I slow it down because otherwise they get frightened. They don't get the chance. Hanji. That is the second part of the question will come. The first is how to test whether it's a reflection of age. Anji? Yeah. So what should you do? How will you show it experimentally? That cells, whatever has happened in the body is also happening. Hayflick limit. Aging of the body will be reflected aging of the cell in terms of this number of divisions. But did you get it what she's saying? She's saying right, which I'm going to agree with. So what did she say actually? Can anybody else just repeat it? Could you hear her? Or whatever you understood it. You please give me your help. So what was the experiment one could do the way she just said it in terms of even cross-sectional study? Feel shy, there is. Otherwise take the help, please help her. Both of you talk about it. Yeah? Because it's an important issue, because you will be using it in your research. That's why we are spending a bit more time here. That if you have to validate a system, that this is the real phenomenon, because that was the question asked to Hayflick at that time. That you say it's aging, what is this to the body? The question is if the body is so aging when we take it out. So if you take, as you said, so say newly born people, 10 year, 20 year, all the way, and you it has something to do with the decisions coming to you, because now I have made it more clear. So what will be if we take the cell, the skin from a little child and a man and an old man or something? Yeah, what do you think? What is the expectation? Will there be a positive relationship or no relationship or negative relationship? Why? Because that was the starting question. So you just come back to that. That was the hypothesis. Because yes, it's true that yes, it's expected that it will reduce, that older the donor, lesser the number of phages in culture. That Jim Smith and Goldstein, which I gave the name. But these kind of experiments, hundreds of samples. You cannot take just reverse results. Studies with hundreds of samples. I get distracted, but it's above 200. Get it? Yeah, or find some. So there are two cell types. Statistically, it was shown that yes, there is a relationship. The relationship is that for every 1 year of life, you lose about 1 population doublings. Yeah. If the maximum from a young person is, and then according to the maximum from a 100-year-old person of life. Simple mathematics, use your otherwise calculators. So what do we expect that how less it should be from a 100-year-old person. How many it should have less? 10 multiplied by 0.2. No, 100 multiplied by 0.2. So, कितनियां कट गईयां divisions? The young 50, so an old person thing will have around 30. 100-year-old person. So, but it's not a very tight correlation, so this has been challenged, but there is a correlation. So, which shows that whatever is happening in the body, then there has to be some evolutionary correlation. कि तुहानू अज जे टाइम ना मिले फिर सानू अगे जाना पएगा चलो पर ये मैं छेती खत्म कर देता दिस phenomena can be being shown in the cell culture. Yeah. If we talk about maximum different. So, Anji. Right. Yeah, this 100-year-old person, what does it mean? Because if it has a maximum ability, now the 100-year-old person's cells are only able to divide 30 times in the same culture medium where cells are dividing 50 times. So what might have happened to cells in that old man? Why did they lose this ability? Resting, but why? So the cell division in cell culture will become less because of apoptosis. That doesn't make any sense to me at least. Why loss of telomere has happened in the body? Okay. No, the answer has to come from the same Hayflick phenomenon. Because telomere loss dividing cells only happens when cells divide. Yeah? So that divisions. So it has already used up. Yeah. Yeah, they have already used it. Question why different cell types from different tissues might have different Hayflick limit, because how many times they have gone through. Immune cells, which are, if you are under infection, they have so many times that when you try to grow them in culture, they might have very few left. Yeah? Now that is the temp on cellular aging. Fascinating. All these questions can be asked, but because it has proteins are getting damaged and there is a certain, and they don't have much repair. Okay, that's a very specific so we couldn't invite him properly. Otherwise, that was the reason I but Rizvi is the newspapers also and whatever, but he's the RBC guy. Yeah, we can talk that a little special case of cellular aging. that can be every explanation, because if we start talking now, that will be going on that. So those are specific cases, and the हरेक दा एडा इशू बन जाएगा ना. हाँ जी, हाँ जी. थोड़ा उच्ची बोलिया करो ताकि दूजे जो सुन सके. वो माइक्रोफोन थोड़े जोगा है नहीं, पर हाँ हाँ जी, हाँ 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 जी. हाँ, aging of the molecules we have to talk about. That's what Gurucharan is going to talk. Chair is aging. Is that the same? But the living system's aging. So those are again, hope we'll talk about that. But the validity of the hayflick system. And you expect that's the starting point. But evolutionary question is even more important. If it has something to do from evolution's experiment is you compare. So what will you study to answer? Otherwise take. That's why I told you our discussions then take 15 days long workshop. You 30 different. No, that's one type you can take. Embryonic stem cells are not stem cells. There are some stem cells are there, but not all of them. Hayflick's work was also done with human embryonic skin fibroblasts. Yeah. Because that was easy abortions, so far the material available was nothing. So he was able to take the skin's fibroblasts from, I think, 20 weeks. I don't exactly remember, but that was a female embryo, female features. So it was easy to take. Because now we do a lot of work like that is from our lab, where we took the skin from the person, and then I think it can be taken from anywhere. Yeah, so I mean, many animals that might be more problematic. So there is 20 species that have taken from almost similar age, from 20 species, and then they grow in the ecosystem, limit. So what do you think was the correlation? Scientific terminology. Yes. Which have short lifespan to have so there is, okay, so scientific way of saying that there will be a negative correlation with age in the cross section of the first one. So here is positive correlation. Longer lived species, higher probability. And that was the validity. That all happened in the 1960s and 70s. So the first generation science was on a combination. Oh, your condition is not right. Your serum or half the experiment. Small effects were visible, but not breaking the age phenomenon. So what else we studied is a relationship then it became very, very important issue in relation to understanding cancer. Because the main difference between a normal cell and a cancer cell became what? We have already talked yesterday. Yeah, the cancer cells are potentially immortal. We don't know they are immortal. At least they don't show Hayflick limit. So then this whole idea came, okay, so if we can cause Hayflick limit to come back into cancer cell, you have a treatment for cancer. So there was this lady, Judy Campisi, who just became second member of the National Academy of America from aging field. Even Hayflick is not a member of that field. So Cynthia Kenyon, who is running Calico, this multi-trillion Google company for aging, and then Judy Campisi, she came in the field and brought all the molecular biology techniques. Okay, hey, there is the answer to cancer therapy basically. That if normal cells become senescent, that means cancer cannot happen. But cancer cells somehow learn how to bypass it. So if we can bring back the same situation either by drugs or by whatever intervention, then you have a cancer therapy. And that is why everybody started working on the field of cancer.
That's called differentiation based.
No, we don't. We call the senescence induction. Different.
Ultimately it brings them into cycles. Once they go back into cycle,
right.
Then they enter into senescence.
So it can be either by inducing telomere or inhibiting telomerase in cancer cells, or by alternative pathways. So that's again the whole field. So that is what made our cellular aging field very, very important. So until Judith Campisi came in picture and brought all the technology of molecular biology, we were still struggling with physiology and biochemistry and all that. So cancer cells escaped the Hayflick limit and developed new characteristics. That understanding came from Hayflick system, from the cellular studies. And basically the role of senescent cells in the body is considered to be is a kind of tumor suppressant. These checkpoint regulations, cell cycle arrest, this is the way the body protects against the formation of tumors and cancer. It's a very important positive role of senescent. Although the senescent cell, which has become old, it might create problems also, but now is the price. If we grow then danger of cancer is much more. But if stop ho gayi hai, so at least evolution needs to stop cancer during essential lifespan. So that was a great achievement of this Hayflick system. Then came that side of senescent cell. Senescent cells body which is still a big issue. That do they exist in the body and to what extent and how do we recognize it? But whenever they exist, they add to this what we call inflammation. Yesterday also Gurchan talked about that the immune system of inflammation is one of the universal characteristics of aging. Okay. Those phenomenon no Italian colleague in terms of inflammation. Inflammation induced whatever else is happening. So it's inflammation. And senescent cells definitely contribute to that. Again, the role of Hayflick system, the use of that. Then this system can be used to modulate different pathways. If you want to play with the kinases or something, so cell culture gives you the capacity to play around with any technology. Even the cells can be brought into stem cells or whichever way you want to do. So cell culture gives you the biggest help for that. And lots of experiments are being done. And also to develop new interventions, new anti-aging products, new pills. First screening can be done at Hayflick model. And that has been used by numerous laboratories, including our own lab. We discovered this kinetin which was affecting the aging of cells in culture. So that there were hundreds of cosmetic products produced by the companies. But starting point was Hayflick model system. So what happened there also. So these were the great achievements of cellular aging system, which is still the most powerful system for understanding aging at cellular and molecular level. But what are its then bad points? Let's quickly have one or two feedback. What are the limitations of this cell culture system? So whatever we learned, again yesterday, Gurchan mentioned that model system tells us some things. Yeah, in her definition she had used an animal, but it can be animal plus cell culture based. But a model system basically means it's a model system. It's not the full reality. It is nearer to the reality. A human cell culture is nearer to the human system than a rat or a mouse or a nematode or a yeast. But then what is the biggest problem with cell culture? Can you imagine something?
So actually, it is a cell. So
ਹਾਂਜੀ.
it is not a system because there is a lot of system, a lot of organs are working together to maintain
Right.
believe that it must require.
Look,
Here we are providing some kind of things that
Yeah.
is essentially
You're absolutely right. So you have saved a lot of time. Because in the body you will never see any place where the cells are growing the way we grow them in the culture. Yeah, they are growing in monolayers, one cell type at a time, millions of cells together. Nothing like that. When you do any histological section, skin da vi cut ke dekh lo ke dermis de vich fibroblasts hunde ne. There will be one fibroblast here and another here and another there. They're never going to be even 10 together or 20 together. But in cell culture, we're creating this huge artificial situation which may never ever be seen in a vivo situation. So one has to remember that even by making our research, we cannot claim, God, kinetin can slow down aging. But that's what the newspapers said. When we talked about it, the world headlines came, the secret to aging has been found, aging will be stopped, and the headline of Times of New York and television started coming. Then Robin Holiday called me on the phone, hey, what is happening? Because he knew that I was working on cell. Because the company was giving up the grant. So for them it was a great thing because immediately everybody will be interested. So that's a different story. But scientists must be aware of the limitation of the system also. Okay, you can't make something. Then important point comes is when we use cell lines. Hayflick used to use the term cell strain for normal cells. For cancer cells that we always use. And these cancer people came in the and then they test some compound and it's growing better or it's moving faster. Oh, it's very good. And then we have to remind them it's very good for the cancer cell, not for the show us for the normal. If you want to have use in aging, then your compound should promote the health of the cancer cell. There it should inhibit or whatever that. So cell strain versus cell line, but we keep using infamously. Nobody uses cell strain, but that's unfortunate. The correct terminology was like WI38 cell strain, which basically created. I did my PhD on the British cell strain called MRC5. Then we made our own cell strain in Denmark, which we call ASS. But it was not a good one. But that was just because I had two clinicians, one was called Annie, other one was called Susanna, and Suresh. Annie. We are made. Senescent cell. Senescent is the second word for extreme aging. When everything has gone wrong, it's bad, that's a senescence. Aging is also the process. Senescence is not the process. Senescence is the phenotype. So, everybody is working on senescence, and we keep reminding that you have to also interfere earlier because in the body cells may never become senescent. Because to become senescent, it needs a lot of revisions, and sometimes it doesn't happen. So, but that's another subtlety details of that. So I was thinking half an hour, but I have taken 1 hour. So let's wind up the cell culture system here. Any questions from at this point? Because these are all various systems which have been used to now study what happens and at what level. So that's what I think Gurcharan is going to talk about in the next 1 hour. But मेरे बारे कोई question? कोई हो? हाँ जी.
So how does the phenotype of the cells change as they usually represent?
How it changes? No, every time a cell divides, it changes a little bit. We still don't know fully. So far, the only correlation we have, which we can measure, that what happens every time the cell divides. There are two things which happen. DNA methylation is getting reduced, and telomere is getting reduced. These are the molecular markers. But that is because you cannot see visually by one division what the change has happened. So, and how that change, loss of telomere, is adding to the spreading of the cell. But that is where all molecular biology comes. That every time they are dividing, they are also getting proteins are getting modified, errors are happening, cytoskeleton is becoming rigid. That's what all that is. There are 900 and whatever, 899 papers people have to read it. But those are no explanations are known, but that we might reach on Monday when we wind up some of these biology parts. I might touch on that.
In this context, are there any data sure like to take the cells from say 60 years old person skin fibroblasts and compare it with the culture which has undergone some regulations and has reached that particular matching state? So the morphology of phenotype doesn't resemble.
Not at the primary culture level. If you take the skin biopsy from an old person, even 120-year-old, well, we haven't taken 120, but there are data from 105-year-old. When they start the culture, which we call primary culture phase 1 in HLA, that you start with skin biopsy and let the fibroblasts grow and make the first confluent, you cannot say any difference visible. They all look the same. Even extreme Bazooka cell, the primary culture, they are able to divide and form the culture. They are all looking. Then when you start subdividing them, subculturing them, that's where the differences start appearing. Okay, from the older person, those differences will come already after 5 or 10 passages. And that primary culture, you should be able to see difference in telomere length. But often it's not, because primary culture means you are selecting for cells which are best growing. So there is a big selection process happening. So we cannot measure at the primary level. But if you grow them, there changes young donor there, एक साल से 10 years, 2 years, 2 3 So it's that kind of thing.
Maybe the senescence marker studies compared with the cells.
Yeah, there are lots of people, that's the biggest problem in cell aging. We don't know how to recognize a senescent cell. In the section for in histology, there are no methods which can show this is a senescent cell and this is not a senescent cell. The only method is what we call Dimri marker. And that's also an interesting story. It's a Govardhan Dimri, he was a GNDU student and then went to America, worked into his pieces there. In 1985, he publishes a paper that he created a stain, beta-glycolysate, it's called the senescence associated. And in those staining, only senescent cells become blue, young cells don't become blue. Yeah. And that's a major, so far that is the only marker which is the kita we looking at. और the story very interesting है कि वो दिवाली में पूछा कि ये तू किਵੇਂ ਲੱਭ ले सारी दुनिया के थ्रू and he found it by being less intelligent simply he was not able to make correct buffers typical Indian student क्या buffer भी नहीं होते बनाना आता था he was doing gene insertion experiments where they need to make a buffer for beta glycosidase assay which works at I think around 7.1 pH पर वो कोई buffer बना रहा थी जिसकी pH जगह 6 point 6 to the lowest and but he didn't know that he was making the mistake and when he was staining the cell young cells and old cells with his buffer only the old cells were getting stained and young cells were not getting stained एक बार किया experiment दो क्योंकि मेरा दोस्त है ਉਹਨੂੰ ਇੱਕ ਵਾਰ ਬਿਠਾ ਕੇ ਅਸੀਂ ਬੋਸਟਨ ਦੇ ਕਾਫੀ ਹਾਊਸ ਦੇ ਕੋਲ ਪੂਰੀ ਕਹਾਣੀ ਸੁਣੀਏ ਵਾਪਰਿਆ ਕਿ ਤੂੰ ਐਡਾ ਜੀਨੀਅਸ ਕਿੱਥੋਂ ਨਿਕਲਿਆ ਕਹਿੰਦੇ ਸੀ ਵਾਹ ਮੈਂ ਬਫਰ ਵੀ ਨਹੀਂ ਬਣਾਉਣਾ ਦਾ ਤੇ ਮੈਂ ਕਿਹਾ ਫਿਰ ਕਿਉਂਕਿ ਸਾਰੀ ਦੁਨੀਆ ਨੂੰ ਰੂਬੀ ਕਪੀ ਸੀ ਦੀ ਡਿਸਕਵਰੀ ਕਰ ਗਈ ਮੈਂ ਕਿਹਾ ਤੇਰਾ ਰੇਸਿਜ਼ਮ ਹੋ ਗਿਆ ਕੰਮ ਤੇ ਤੂੰ ਕੀਤਾ ਕਹਿੰਦੇ ਕੰਮ ਤੇ ਮੈਂ ਕੀਤਾ ਕਿਉਂਕਿ ਮੈਂ ਗਲਤ ਬਫਰ ਬਣਾਇਆ 3 ਵਾਰ 4 ਵਾਰ ਕੀਤੇ ਉਹੀ ਆਉਂਦਾ ਸੀ ਉਹ ਜੂਡੀ ਨੇ 4 ਵਾਰ ਦੇਖਣ ਤੋਂ ਬਾਅਦ ਕਰੀ ਕਿ then there is something important here whatever you are doing even by mistake but then why it is not staining all cells only some cells are stained in that and then that's where the genius comes her intellectual jump there's some difference in young and old and your stain is picking up let's do it now systematically फिर जो उन्होंने pH ਨੂੰ every point ਦੀ variations ਕਰਕੇ ਲੱਭਣਾ ਸ਼ੁਰੂ ਕੀਤਾ ਤੇ ਫਿਰ ਪਤਾ ਲੱਗਾ ਕਿ ਇੱਕ ਖਾਸ pH ਉੱਤੇ that was a very important phenomenon ਫਿਰ ਉਹਨਾਂ ਨੇ skin ਦੇ sections human skin ਦੇ ਦੇਖੇ then they were able to show that senescent cells exist in old skin not in young skin and that paper in GNDU from 1995 I think that has about 20,000 citations so far because everything is based on still we use that as a marker of cellular aging for every paper you publish you have to use that people have tried other markers P16 P21 DNA damage foci there are 3-4 so that is still the marker but it's not a universal marker it has some problems still so sometimes being stupid making mistakes is very good you don't have to be always right that's what it says and don't be afraid of making mistakes you cannot make mistake deliberately because then it's not a mistake mistake is always by chance ਤੇ ਉਹ ਚਾਂਸ ਕਈ ਵਾਰ ਮਾੜੀ ਐਜੂਕੇਸ਼ਨ ਵੀ ਤੁਹਾਡਾ ਸੋ ਡਿਗਰੀ ਵੀ ਅਮੀਰ ਬਣ ਗਿਆ ਹੀ ਹੈਜ਼ ਬਿਲੀਅਨਸ ਆਫ ਡਾਲਰ ਕਿਉਂਕਿ ਉਹਨਾਂ ਦੀ ਮੇਰੇ ਕੋਲ ਕਿਹੜੀਆਂ ਕੰਪਨੀਆਂ ਨੇ ਉਹਨਾਂ ਦੀ ਕਿੱਟ ਤਿਆਰ ਕੀਤੀ ਤਾਂ ਯੂ ਕੈਨ ਬਾਈ ਦ ਕਿੱਟ ਐਂਡ ਡੂ ਦੈਟ ਤੁਸੀਂ ਵੀ ਜਿਹੜੇ ਸੈਲੂਲਰ ਰੇਜਿੰਗ ਦੇ ਕੰਮ ਕਰਦੇ ਹੋ ਯੂ ਵਿਲ ਹੈਵ ਟੂ ਸ਼ੋ ਐਟ ਸਮ ਸਟੇਜ ਦੈਟ ਯੂਰ ਸੈਲਸ ਆਰ ਇਨ ਸੈਨਸੈਂਟ ਫੇਜ਼ ਔਰ ਨੋਟ ਐਂਡ ਦੈਟ ਬੀਟਾ ਕੈਨ ਉਹਨੂੰ ਕਹਿੰਦੇ ਸੈਨਸੈਂਸ ਐਸੋਸੀਏਟਡ ਬੀਟਾ ਗਿਆ ਸਾਫਟ ਆਓ ਜਾਓ ਔਰ ਟੇਕ ਦ ਬ੍ਰੇਕ
Take the break.
Take the break but continue privately. Yeah.
Sir, same kind की प्रॉब्लम हमें रैट्स में आती है कई बार हमने रैट आइसोलेट कर देते टाइम लगा था ये इसका रैट है जैसे 2-3 मंथ का है 4-5 मंथ का है 10-11 मंथ का है तो कई बार वो टैग खा जाते हैं डिफरेंशिएट कैसे करें कि हमको किस एज का है तो ज़्यादा तो एज का बाय वेट पता लग जाता है कि जैसे ये बन गया ये हो गया वेट बढ़ गया लेकिन particular नहीं होता
That is no way.
ਇਸ ਤੋਂ ਪਹਿਲੇ ਮੈਨੂੰ ਦੱਸੋ ਕਿ ਤੁਸੀਂ ਮੈਨੂੰ ਕਿੱਦਾਂ ਐਕਸਪਲੇਨ ਕਰਦੇ ਹੋ ਕਿ ਮੈਂ
ਸੁਆ ਦਾ ਟੈਗ ਖਾ ਗਿਆ ਉਹ ਫਿਰ ਉਹਦਾ ਇੱਕ
ਮੈਨੂੰ ਨਹੀਂ ਅੱਜ ਤੱਕ ਦੱਸਿਆ ਕਿ ਤੁਹਾਡਾ ਟੈਗ ਖਾ ਗਿਆ ਤੇ ਅਸੀਂ ਹੁਣ ਐਕਸਪਲੋਰ ਦਾ ਕੰਮ ਕਰ ਰਹੇ ਹਾਂ
ਉਹਦਾ ਫਿਰ ਇਹਨਾਂ ਕੋਲ ਇੱਕ ਠੀਕ ਹੈ ਟੈਸਟ ਬੜਾ ਵਧੀਆ ਉਹ ਟੈਸਟ ਹੈ ਫਿਰ ਸਾਰੇ ਚੂਹੇ ਨੂੰ ਇਹ ਛੱਡ ਦਿੰਦੇ ਨੇ ਖੁੱਲਾ ਤੇ ਏਜਿੰਗ ਨਾਲ ਬੁੱਢਾ ਚੂਹਾ ਜਿਹੜਾ ਹੈ ਥੋੜਾ ਸਲੋ ਹੋ ਗਿਆ ਉਹ ਜਿਹੜਾ ਚੂਹਾ ਤੇ ਖੜਿਆ ਗਿਆ ਫਟਾਫਟ ਉਹ ਹੈ ਬੁੱਢੇ ਚੂਹੇ ਜਿਹੜੇ ਨਹੀਂ ਕਾਬੂ ਆਏ ਹੋ ਯਾਰ ਇਹ ਤਾਂ ਸਾਰਾ ਟੈਸਟ
ਨਹੀਂ ਉਹ ਕੋਈ ਹੈਲਥ ਸਪੈਚ ਵੀ ਹੋਏਗਾ ਤੇ ਉਹ ਵੀ ਪੰਗਾ ਫਿਰ
ਇਹ ਇੰਜੀ ਹੁੰਦਾ ਉਹ ਅਸੀਂ ਡਿਸਕਸ ਕਰਾਂਗੇ
ਕੋਈ ਵੀ ਬਾਹਰ ਹੈ ਰਿਫਰੈਸ਼ਮੈਂਟਸ ਆ ਗਈ
Sir, I have a question. There is a warning or there is something ultimate that is sensing that